Hi, this is lecture one in chapter five, which is the design of eccentric shear connections. Eccentric means the connection has eccentricity. Concentric means the forces are acting in the CG of the connection or CG of the group of bolts or CG of the connection in general. In the previous course in the design and the structural analysis course of basics of structural analysis, chapter 21 discussed eccentric connections, and I'll just give you a very brief review of what we ended up with chapter 21 of the previous course when we talked about connections subject to torsion. We talked about the critical bolt concept. We said that if the forces are acting in the CG of the bolt group or CG of the welds, each weld is taking equal share of the load, and each bolt is taking equal share of the load. So the load in the bolts is the number of the total load divided by the number of bolts in the x direction and in the y direction. But if we have eccentricity, like if we have a bracket connecting a beam to a column, let's say. So at the bracket, we have bolt group, but we have the forces at the top of the bracket, top left corner. So in this case, we'll share the screen quickly to show you this one. So in this case, we have eccentricity. In this case, we have eccentricity on the bolt group because we have the forces and the moments. So the forces are transmitted to the CG of the bolts plus moments. This moment B multiplied by this distance minus H multiplied by this distance, which means that the bolts are not sharing the load equally. Each bolt is taking different load. Okay? And we talked about crane. We said that this is the bracket of the crane that transmits the loads to the columns. What are the different failure mechanisms? We said there are four possible failure mechanisms for this connection. One, shear failure in the critical bolt, and the second one is bearing failure in the plates. The third one is shear failure in the plates, and the fourth one is normal failure in the plates. So three related to the plates and one related to the bolt. So first failure mode or mechanism or possibility is shear failure in the critical bolt, and three other failure scenarios or possibilities or mechanisms. They are related to the plate: bearing failure in the plates, shear failure in the plates, and normal stress failure in the plate. And then just review the critical bolt before we move to the next to chapter 5, which is the simple connection. So if we have the same connection that we have here, this B and H at the tip of the bracket, and the CG of the bolt group is over here. So the loads are transferred as B, H, and moment. Okay, so this is step one. Step two to transfer. Step three is to get the resultant of the bolts. So here we have the bolts coming out of the forces coming out from end torsion. Okay, and the forces coming out from the X and Y or from the resultant. Okay, so the forces coming out from the resultant. Okay, so over here we have a critical bolt, which is this one, which has the force coming out from the resultant is adding to the force coming out from the torsion. So this is the force coming out from the resultant, which is this one. They all have the force in this way, which is in the resultant. And this one has the two forces, the one coming out from the resultant is B and H, and the one coming out from M torsion, they are added up, so this is the critical bolt. So if we design the critical bolt and make sure that the critical bolt is safe or adequate, all other bolts, assuming that they have the same diameter and properties as this one, are safe. So this is where, and then we've solved many examples related to this. Today we're going to discuss or talk about connections, eccentric connections subject to torsion, and this is chapter 5 in the course, in the steel design course, design of eccentric connections subject to torsion. Okay, what are eccentric connections? These are connections at which the forces and the moments. These are connections that have forces and moments acting on them. And these moments could be bending moment or torsional moment. And the resultant of the forces, it is not in the CG of the bolt groove, or it's not in the CG of the weld groove. So there is eccentricity between the force location and the result, and the location of the resultant, or CG of the bolt, or CG of the weld groove. So there is eccentricity. So they usually have forces acting on them in the X and Y direction, bending moment, and sometimes torsional moment. Before studying this eccentric connection, we have to review some concepts like straining actions affecting any section and how to calculate the straining action. So before we start talking about, you'll find some similarity and some repeated stuff from the previous course. Okay, some review of the previous course of the basics of structural analysis. Okay, and some is new material, and some is related to crane girder and cranes, design of crane brackets and crane connections to columns and so on. So before we study these connections, we have to review the straining actions affecting any section and how to calculate them. We have to study them and show how to calculate them. We have studied the straining actions, and these are the forces that are possibly acting on the section. And the straining actions are 6 forces in general. So we'll share the screen, show you these ones. So the straining actions, let's say that this is a section of a beam or a beam element, or a beam element or an arch element. So the section is rectangular in this case. X-axis is the x-axis, and y-y is the y-axis, z-axis outside the page, outside the section, perpendicular to the section. So what are the straining actions acting in the section or possibly acting in the sections? There are 6 of them. In the normal force, tension or compression, Q shear force positive or negative, and Q shear force in the Y direction, Q shear force in the X direction, bending moment mx about X axis, either tension side up or tension side down, bending moment about Y, either tension side left or tension side right, and torsional moment about the z-axis, which is the longitudinal axis of the member, or the axis perpendicular to the section. So we have M torsion clockwise and M torsion anti-clockwise. So these are the possible straining actions for the section. And due to these straining actions, 2 kinds of stresses are generated. Okay, one is normal stress and 2 is shear stress. So the normal stresses are coming out. So the normal stresses, they are either tension or compression in the section, and they are coming out or produced or generated from the normal force bending mx, bending my. So normal force bending mx, bending my. These are the straining actions that will cause normal stresses, either positive or negative, either tension or compression. So this is N tension, this is N compression. This is the compression side for mx, and this is tension side of the mx. So compression at the head of the arrow, and tension at the tail. Tension at the tail, which is above over here, and compression is at the bottom. My, it could be either this way or that way. So here tension is on the right, compression is on the left. Here compression is on the right, tension is on the left. So normal force mx and my cause normal stresses. So the compression is at the head of the arrow, and the tension is at the tail of the arrow. And for tension force, when the force pulls out the section, it is tension. When the force compresses the section, it is compression. The other type of stresses, which are shear stresses, and they are produced by one or all of the, or a combination of the following: Qy, Qx, and Mz. So shear stresses, they are generated due to friction with the section. So the forces are parallel to the section. So either this force or that force, or torsional moment. So this force Qy, this force Qx, or torsional moment also produces friction, produces shear stress. So Qy, it produces shear stress, shear force. It acts along the area of the section. Qx acts along the area of the section in the x direction, and Mz, torsional moment, this way or that way, they act along the surface, so they also cause friction, they also cause shear stresses. An important note, the force which is parallel to the axis and or cuts the axis do not cause moment about this axis. Okay, so if the force is parallel to x-axis, it doesn't cause moment about x-axis, it causes moment about y-axis. Okay, and when it cuts it, it could cause moment, but it cuts it, it means the arm distance is zero, so it also doesn't create moment. Example, we have this section, x and y axis, where P at a distance A in the Z direction. What are the straining actions for this section? Normal force is zero, Qx is zero, Qy equals minus P or P down, Mx equals PA this direction, clockwise, My is zero, Mz is zero. Because it cuts Z, if it is at a distance from the Z in the X direction, then it will cause torsion. But it is just active on Z, so it doesn't cause moment about Z. And it is parallel to Y, so it doesn't cause moment at Y either. So it only causes moment about X. So these are the stresses. These are the normal stresses in Mx and Y. And these are the shear stresses Qx, Qy, Mz. Example, what about this section? We have P at a distance B from Z. It acts away from the section at a distance A from the section at a distance B from Z. Now it causes moment about Z. So normal force is zero, Qx is zero, Qy is P down, same thing. Mx equal PA, same thing. The difference is this one causes Mz, which is P by B, My equals zero. So here there is Mx and Mx causing normal stresses, and Ty and Mz causing shear stresses. Okay, another example. What are the straining actions of this section? We have this section X and Y. We have the load P at a distance A from the surface, or distance A from X, distance B from Z, and distance C down from Y. Okay. No. There are two forces. There is F, this is not K, there is F over here, yeah, exactly. There is F over here that's acting at this point, which causes My. And there is P, which causes Mx and Mz. So normal force equals K, and there is K also acting along Z. So K, P, and F. So this section has three forces outside the section. K causes compression. So M equals K equals compression. Qx equals F in this direction. Qy equals P down. Mx equals P multiplied by A. My equals F multiplied by A. P by A equals Mx. F by A equals My. Mz equals PB plus FC. PB plus FC. Okay. So now we'll just study the straining actions on different sections coming out from different forces at different locations. Eccentric connection subject to torsion and eccentric connection subject to bending. What is the difference between connection subject to torsion and the one subject to bending? The one subject to torsion, the forces and the moments are in the same level of the connection. So the one subject to torsion, they are all acting at the same level of the connection because they are causing shear. So the center connection subject to torsion, in this one, the forces and moments are acting in the same plane of the connection. So we have X, Y, and Mz. They are all in the same plane of the connection. But for bending moment, as a connection subject to bending moment eccentric, we have forces outside the surface and forces outside, and moment even outside the plane of the section. So for the forces forces and moments are perpendicular to the plane of the connection. In torsion case, forces and moments are in the same plane of the connections, but if they are subject to bending, forces and moments are in a plane perpendicular to the connection surface. So this is the plane of the connection. For the torsion case, we have shear force in the same plane of the connection, torsional shear forces in the same plane of the connections, torsional moment in the same plane of the connection. In bending moment, we have normal force perpendicular to the connection, we have bending moment perpendicular to the plane of the connection. In section subject to torsion, we have shear stresses due to shear force and torsional moment. And in eccentric sections subject to bending, we have normal forces and bending moments to normal stresses. We have shear stresses and torsion related to torsion and normal stresses due to bending. So in eccentric connection due to torsion, we have shear stresses. In eccentric connection due to bending, we have normal stresses. Okay, eccentric connection subject to tension, bolted connection. So we will start with eccentric connection subject to torsion, which are bolted connections, not welded connections. Okay, so if the shear force is acting at the CG of the bolts, then the forces are divided equally by the bolts. Like this is what we studied in the structural analysis course, chapter 21, which is the effect force. So the forces are divided by, or the bolts are taken the forces equally. So each one is taking the force in the A and the B multiplied by the number of bolts, and H multiplied by the number of bolts. This is what we studied before. This is in case of the forces are acting at the CG of the bolt groove. This is the elevation and this is the plan. Two brackets in each side. These B and H are half on this side and half on that side. Or they are taken by 16 bolts, 8 on this side and 8 on that side. So these are the forces in the column down or in the bracket going to the column. So these forces are taken by two brackets by say 8 bolts on this side and 8 bolts on that side. So if unless we say that B and H are on each face. If B and H are on each face, so each bolt in this case is taken B by 8 and H by 8. On this side, they are taken B by 8 and H by 8. So they are on each side, they are on each bracket. So the 8 bolts here are taken each 1/8 of the H and 1/8 of B, same thing on the other side. Okay, so each bolt will take B over 8 and H over 8. B and H are on one side. Okay, then each bolt is like this, have H over 8 horizontally and B over 8 vertically. This is in case B and H are acting on this gusset, and this is B and H acting on the other gusset. If the forces are not acting at the CG of the bolts, what happens? What happens if the forces are not acting at the CG of the bolts? What happens is the force is not distributed equally to the bolt. Which means that there is torsional moments in the bolts in addition to the applied forces. So this torsional moment creates unequal distribution of the loads. Okay, so here we have this one, the same gusset. We have B and H on each side of the bracket. Looks like it's on each side because we're only dividing by 8. So B or vertical, H horizontal. I'm thinking loud. I'm thinking like I'm putting myself in your situation and saying, why did we divide by 8, not by 16? And the reason is V and H are only on one side of the bracket. So V and H are only on one side, so they are only divided by 8 bolts, and here is V and H on the other side divided by 8 bolts. So here V and H are not at the, this is the CG of the bolt groove. So here V and H are not acting at the CG of the bolt groove. So they are acting with eccentricity. So there is torsion in the bolts. The bolts are like this. And V and H cause moment about the longitudinal axis of the bolt. So they cause torsion on the bolt. So this is the elevation, this is the plan. To know or to determine the forces acting on each bolt, we do the following. We move the forces from their location to the CG, and every force is moving by force and a moment, and a torsional moment in the bolt. To calculate the torsional moment, we take moment about the CG. We calculate the horizontal force and vertical force on each bolt in addition, and they are the summation of the forces transferred to the CG in addition to the share of the torsion. Okay, what is important to us is the critical bolt, which is the bolt that has the maximum forces, the maximum resultant force. And then we have to calculate the maximum or resultant force on the bolt. You see the one that has the maximum resultant force, and it's called the critical bolt. And if we design for this critical bolt, make sure that this bolt is safe, then everything else is safe. Make sure that this bolt does not fail, then other bolts will not fail. So this is a bolt that has the resultant of the horizontal and vertical forces in the same direction, adding up in the same direction of the torsional moment force. Torsional moment forces are acting on the bolts, and they are like perpendicular force to the axis of the member. So eventually it is the shear force on the bolt. And we're going to show you how to calculate this one. Again, this much has been studied in the previous course in the basic structural analysis, chapter 21. For those of you who have not taken the course, this is new material, but for those of you who have taken the course, this is the partially review of what we talked about before, what we discussed before and solved it before. So effect of torsional moments on the bolts. Here we have M torsion, okay? So we have, this is the CG group of bolts. This one is at Y2, this one is at Y1, and this one is at X, and this one is at X. So the bolts over here have X coordinate, over here have X coordinate. This row has Y2, and this row has minus Y2 plus Y1 minus Y1. So the torsional forces are forces perpendicular to the radius, which is the line connecting from the bolt to bolt to the CG of bolts. This is the radius of rotation, and F1 is this one. So here we have F1 at R1 and F2 at R2 and F3 and R3. And then again F1 R1, F1 R1, F3 R3, F2 R2, F1 R1. Okay, so we have this bolt. We have F1 resultant H1 and B1 at the distance R1 and angle alpha. This one is X, or X1, X actually because they all have X, or minus X, and Y1. So sine alpha equals Y1 over R1, cosine alpha equals X over R1 or X1 over R1 in general as a general equation. MT is shared by the group of bolts as the function of small moments. So F1 by R1, F2 by R2, F3 by R3. Okay, so F1 over R1 equals F2 over R2 equals F3 over R3. So the share of F1 of the moment divided by the share of F2 is the radius of R1 divided by the radius of R2. Okay, M torsion equals summation of F1 R1 plus F2 R2 blah 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 plus Fn Rn. In this case, 8 groups plus F8 R8 in general plus Fn Rn. And the other equation that these both groups have is F1 divided by R1 equal F2 divided by R2 equal F3 divided by R2. So we have two equations. From equation 1, F2 equals F1 R2 over 1, F3 equals F1 R3 over 1, F4 equals F1 R4 over R1, and so on. Substituting one, we end up with one equation in F1 which is M torsion equals F1 R1 plus F1 R2 over R1 multiplied by R2 plus F1 R3 over R1 multiplied by A3 and so on. So M torsion equals F1 R1 plus F1 R2 square over R1 plus F1 R3 square over R1 and so on. Then M torsion multiplied by R1 equals F1 R1 squared plus F2 F1 R2 squared plus F1 R3 squared. Then M torsion multiplied by R1 equals F1 multiplied by R1 squared plus R2 squared plus Rn squared. Then M torsion multiplied by R1, M torsion multiplied by R1 equals F1 summation of R squared. Or F torsion equals M torsion R1 divided by summation of R squared. This is F1 force. I think if we get F2 related to F1 by this equation, F2 related to F1 from this equation and so on. So we get F1, you know, on torsion, we get F1 and then substitute in these equations to get F2, F3, F4, and so on. H1 equals F1 sine alpha. H1 equals F1 sine alpha. Or MT R1 over sigma R squared multiplied by 1 over Y1 over I1, or H1 equals MT Y1 over sigma R squared. V1 equals F1 cosine alpha, which is sigma M torsion divided multiplied by R1 divided by sigma R squared multiplied by X1 over R1. Or V1, which is the horizontal component of the shear force related to torsion, is M torsion X1 over R square over sigma R square. So H1 vertical component of forces due to torsion, H1 at bolt 1 is M torsion Y1 divided by sigma R square. V1 is M torsion X1 divided by R square. How to determine the critical bolt? We determine the direction of the horizontal force, determine the direction of the vertical force, determine the direction of the resultant of the forces, then determine the direction of the forces on the bolts due to MT. And it is a perpendicular line to the radius, which is the line connecting between the bolt and the bolt group CG, and runs in the same rotation of MT. The critical bolt, which is the bolt at which we have the resultant of the horizontal vertical force in the same direction of the load coming out from torsion. So we have this elevation, Qx and Qy over here, 6 bolts. So we convert it to this one, Qx and Qy, not at the tip, at the CG of the bolts plus MT. We have at each bolt this X component and Y component, resultant component. So we have this X component, this is X divided by the number of bolts. Y component, Y divided by the number of bolts. And this is the resultant, which is X divided by the number of bolts, and Y divided by the number of bolts, the resultant of the two forces, vectorial resultant. So we have due to torsion. This is the torsional moment. So the forces are like this, perpendicular to this radius. This, perpendicular, this. Okay. So again, these are the forces due to MT. And over here, the resultant is this one. At this location, we have the resultant of the force, and the resultant of the force due to MT are in the same direction. So this is the critical bolt. So this is how we determine the critical bolt for this bolt group. The outside forces or the exterior forces acting on the connection are Qx and Qy, which are the ones causing torsion. So the forces acting on the bolts are not equal. And the bolt that is subject to the biggest force is the bolt that will first fail due to this connection. It is called the critical bolt because this is what determines the design of the connection, the design bolt of the connection, this failure mechanism, which is the shear failure in the bolt. If this one fails, the whole connection fails. If this one is safe, every other bolt is safe, nothing will fail, then the connection is safe regarding this failure mechanism. Now we have learned how to define the location of the critical bolt, and now we're going to see how to get the resultant in the critical bolt. Okay. To determine the CG for the bolts, considering them like circles, which is the circle of the area of the bolt, whether it is the threaded area or the unthreaded area. So areas, just round circles, 6 round circles, x and y of the group of the circles, and CG is the intersection of x and y of the group of the circles. Okay, which is the axis of symmetry, intersection of the axis of symmetry, x and y will give you the CG of the bolt group. We have to move the forces to the bolt group or to the CG of the bolt group. Okay, knowing that the force will be transferred by a force and moment, and summation of the moments is MT. So here, numerical example, we have CG 6 volts, 60 centimeter and 20 centimeters. This is 56 ton down, 24 ton in the positive x direction. So these forces will be moved to the bolt group at 36, and this one is 36, and moment 36 by 60. And this horizontal one will move to the bolt group by a force and moment. Force is 24 and moment is 24 by 20. So both of them will move to the CG with the force 36 down, 24 positive right, and combined moment, which is a torsion, which is 36 by 60 plus 24 by 20. 56 by 60 plus 24 by 20, which is 2640. So 36 down, 24 positive right, or right direction, right x direction, and a moment of 2640 centimeter time. So these ones have been moved to this location with the same forces and a moment, same forces, same direction and a moment, and we calculated this moment as 2640 centimeter time. So this is how we transfer the load from their original location to the CG of the bolt group. Then we have to distribute the loads on the CG, which are the loads and moments, 36 ton down, 24 ton in the positive x direction, and 2640 centimeter ton clockwise moment. We have to distribute them on the bolts. First, we distribute the 30 ton, the 36 ton vertical on the bolts equally, and then distribute the 20 ton horizontal in the bolts equally. So here we have 6 ton vertically, which is 36 by 6, assuming this is for one side for one bracket, these loads. So vertically, each bolt will carry 36 by 6, which is 6. Horizontally, each one will carry 24 by 4 by 6, which is 4 in the same direction of the original load. So these are not actions, these are just the distribution of the forces on the bolts. So this bolt is carrying 6 down and 4 right, 6 down and 4 right, same for all of them. They carry the loads equally, but the inequality will come from the frictional moment. Then the second step is to distribute the moment, 2640 centimeter ton on the bolts. Like this, we have F1 R1, F2 R2, F2 R2, F2, 3, 4, 5, F6, R6. I mean, we know that these are equal, F1, 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 and F2, F2, because they are at equal distances. But in general, they are F1, F2, 3, 4, 5, 6, in general. So we distribute the, so now this one is like this. These are the forces torsion. This one has a resultant like this. All of them have a resultant in this direction. So this is the only bolt that have the forces additive. The resultant from this one and the resultant from this one in the same quarter. Okay, which is the right lower quarter, right and lower quarter. So this is the critical bolt because it has the forces due to x and y and have the forces due to torsion in the same quarter, in the same direction. Okay, so this is the critical bolt. We have H1 and V1 over here due to this F1. H1 equals M torsion multiplied by Y over sigma R square, and V1 equals M torsion multiplied by X of this bolt divided by sigma R square. Then we calculated the H1 and V1 for this one. We calculated H and V for this one. Sum up H, sum up V, and then get the resultant. Square root V total square plus H total square. That's one way. Or have this resultant, and get resultant of the two. Or easier yet, what we said is add H1 to this H, V1 to this V, and get H combined, H total, B combined, B total, get the result. So to get the final force in the box, we add up the horizontal